there, young students of chemistry. So we are back looking at our models of the atoms, and kind of where we left off was Bohr's model of the atom, who had this planetary model. He was describing the electron movements as orbiting the nucleus of the atom in a set path. And what we're looking at now is the modern model of the atom, which is like Bohr, and that it says that the electrons in the atoms are still quantized. So Bohr said the electrons are quantized, and that's what he was explaining with the emission spectrums. Like, why did he only see 4 lines of color when he refracted the light from the hydrogen gas? So the modern model is similar to that, in that they say electrons are quantized. However, it does not define a specific path of movement for the electron. So the electron is free to move around the nucleus. And what we do is we say that the region of space where the electron is moving in is called an electron cloud. An electron cloud is just a region where there is a probability of finding an electron. It is a high probability, 99%. So an electron cloud estimates the probability of finding an electron around the nucleus of the atom in a particular space. So I would encourage you to pause this as need be to get your notes. But we're gonna chug on through here. So here's the thing, electron clouds can be described using 4 quantum numbers, and this tells us kind of how the electrons stack themselves outside of the nucleus and around the nucleus, so that they are all feeling the maximum effect of the nucleus. They are in particular positions. So the first quantum number is called the principal quantum number. Its little variable, or the little symbol for it, is an N. I'm going to call that energy level. These are integers, 1 through 7 typically, and they tell us how big the electron cloud is. So keep in mind that if the electron cloud is really, really large, the electrons that are in that electron cloud are far away from the nucleus of the atom. So it kind of tells us the size of the electron cloud, or the orbital that those electrons are in. The angular momentum quantum number I'm going to call the sublevel. That describes the shape of the orbital, and there are 4 different shapes that we are going to concern ourselves with: the S, P, D, and F. And I'm going to show you a picture here. You can see that the S orbital in the upper left-hand corner there is a spherically shaped orbital, a spherically shaped electron cloud. The P orbital kind of looks like an hourglass. And you can see that you can have a p orbital on the x-axis, a p orbital on the y-axis, and also a p orbital on the z-axis. And all of those can come together into one sublevel. So when it says all of the p orbitals are full, that's all 3 of those orbitals in one sublevel. So these are just a picture. You don't have to know necessarily what the d orbitals look like or what the F look like, but S and P, I would think that that's something that is very achievable. So here's the thing about the S, P, D, and F orbital sublevels. They have a particular number of orbitals, which is described by the angular momentum quantum number. So it's really the number of orbitals that can kind of position themselves along the axis and still be separate orbitals. So the numbers of orbitals in the sublevels are 1, 3, 5, and 7. They're easy to remember because they go up by odd numbers. So you kind of have to put in your head sublevels, S, P, D, F, orbitals 1, 3, 5, 7. So the 1 corresponds with the S sublevel. The S sublevel has 1 orbital, the P has 3, the D has 5 orbitals, and the F has 7 orbitals. So the last quantum number, and this is not written in here, is the spin. When an electron is moving, it creates a little bit of a magnetic field. So we say that, oh, these electrons are spinning in opposite directions. So the spin quantum number is defined as either plus 1/2 or minus 1/2. And those will tell you, that really just tells you that in order for two electrons to be in an orbital together, they have to be spinning, what they would say, in the opposite directions. We would indicate that with oppositely facing arrows representing the electrons with opposite spins here. So here's the thing. What this boils down to is that the spin only allows for two electrons in any orbital. You cannot have more than two electrons in an orbital because there are no more spins other than plus 1/2 and minus 1/2. So that's kind of about what you need to know with the quantum numbers. Again, you don't need to know the names except maybe the principal quantum number, but I'm going to call them energy levels, sublevels, orbitals. Energy levels, sublevels, and orbitals. So we're going to use energy levels, sublevels, and orbitals to describe the placement of the electrons. The placement of the electrons are called electron configurations. The electron configuration is kind of a map of the electrons around the nucleus of the particular atom we're talking about. So these are the rules that we use to govern the writing of electron configurations. I'm not real big on knowing, who is associated with what, but this is in the curriculum, so I'll provide that for you. So Aufbau says electrons will enter the lowest energy level first, which makes sense. Those lower energy levels, electron clouds at the lower energy levels, are closer to the nucleus of the atom, and there's a force of attraction between the negative electron and the positive protons that are in the nucleus of the atom. The Pauli exclusion principle is based on spin, only two electrons in any one orbital, and Hund's rule says that electrons are not going to pair themselves unless they have to change to another energy level. So in order to avoid going up in energy, the electrons will pair themselves, but if they don't have to, they won't. So we'll put one electron in an orbital before we pair up. This is what an electron configuration looks like. So you should have out your periodic table, and we're going to start writing electron configurations in a minute. But if we look at this, we can see that an electron configuration has coefficients. Here it's 1, 2, and 2. Those are the energy levels. Those are the principal quantum numbers. An electron configuration also has lowercase letters, S, S, and P. Those are the sublevels. Those are the shapes of the electron clouds. And then it also has superscript numbers, 2, 2, and 4. Those are the electrons. So we know, looking at our periodic table, that oxygen has 8 protons and 8 electrons. If we add these electrons together, 4 plus 2 plus 2, that gives us 8 electrons. So that is what an electron configuration looks like. And I'm going to show you how to use your periodic table as a tool for writing the electron configuration here. So an orbital diagram is a little bit different. Remember, orbitals 1, 3, 5, 7, so SPDF 1, 3, 5, 7. S sublevels have 1 orbital, P's have 3, D's have 5, and F's have 7. If we're writing an orbital diagram, it's kind of like an expanded electron configuration. We're going to draw horizontal lines to represent an orbital. So if you have an S sublevel, you would draw 1 horizontal line. If you had a P sublevel, you would draw 3 horizontal lines. That represents the P sublevel, P orbital that's on the x-axis, the y-axis, and the z-axis, and so on. And then you would draw the electrons in with oppositely facing arrows. So if we want the orbital diagram for oxygen, we know that we have an S sublevel at the first energy level, so 1s, and there are 2 electrons in there, so I'm going to put an up and a down arrow in the 1s orbital. So the next sublevel is second energy level, an S sublevel with one orbital. That's why I have one horizontal line. And again, there are 2 electrons in that particular orbital. The next electrons are in the 2p. So because it's a p sublevel, right, I have to draw 3 lines to represent the 3 orbitals of the p sublevel. And in there, I'm going to put 4 electrons. So I'm going to put 1 electron in each orbital first, and then I'm going to go back and pair. So that's what an orbital diagram looks like for oxygen. Okay, using our periodic table as a tool for writing electron configurations, the first thing I'm going to do is I'm going to move this electron over here. So electron number 2 is going to be over here on the periodic table. So for this purpose, the boxes just represent electrons. The periods, if we number those down, 1, 2, 3, 4, 5, 6, 7, those are going to represent energy levels. I'm going to number this side too. 2, 3, 4, 5, 6, 7. And then the different sections of the periodic table are going to represent sublevels. So you can see that the periodic table naturally has 4 sections, and there are 4 sublevels. This is not a coincidence. This is because the elements are placed according to their properties. The properties of an element and the way they react are completely dependent on how their outer electrons are. So if we look at our periodic table, we have this section would be our S-filling sublevels. Oh, darn it. This section to the far right would be our P-filling sublevels. The center, where the transition metals are Ds. And then the lanthanide and actinide series, those intertransition metals on the bottom, are F-filling sublevels. So if you remember SPDF 1357, S sublevels have 1 orbital, and there's 2 electrons for every 1 orbital. So I'm going to use a highlighter here. Okay, apparently I cannot get the highlighter that I was looking for. So the S-filling sublevels have 1 orbital and 2 electrons. We will represent each of those, right? So in the S-filling sublevel here, right, 1, 2 electrons. 1, 2, 1, 2. S sublevels have a maximum of 2 electrons because there's only 1 orbital. If we move over here to the P sublevels, count how many boxes there are. P sublevels have 3 orbitals, SPDF 1357, and there are 2 electrons per orbital. 3 times 2 is 6. Look, 1, 2, 3, 4, 5, 6. And it's that way all the way down. There's 6 boxes here representing 6 electrons. The D sublevel has 5 orbitals for a total possible 10 electrons. And if we count here, there are 10 boxes on each of these rows, representing the 10 electrons that fill the D sublevel. So if you're following along, you might be getting it. Okay, well, the F sublevel then has 14 boxes, and it completely does. The F sublevel here, 14 boxes representing a total possible of 14 electrons. It doesn't have to be full, but you can have no more than 2, 6, 10, and 14 electrons in those orbitals. So what we're going to do is just count. Here's the rules. We're going to fill the electrons, always starting with electron number 1, which is right here. Oops. And always going in chronological order. So after electron number 2, we have to do electron number 3. After number 4, we have to go over here to number 5. We must go in chronological order. So those are kind of the big rules here. And then the other thing to remember is that when we get to the D sublevels, Like the D sublevel, for example, if we're considering scandium, where the D sublevel starts, we would say that, oh, well, this is energy level 4 for these S sublevels. The D sublevels are one energy level less than the S sublevel before it. So this is not 4D. This is 3D here. This is 5S, but this is 4D. This is 6S, but this is 5D. And it's true also for the F sublevels. Element number 57 really belongs in here. And the F sublevels are 2 energy levels less than the period that they're in. So really, if we're going in order, this is going to be 6S, 2, 1, 2, right? 1, 2. And then you come down here to element number 57, which is in period, which is an energy level 4, sublevel F, 14. And then back up here to 5D, 10. So it's a little more difficult showing you this way without you being here, but I'm going to kind of draw the electron configuration as I go. So at this point, you should probably just kind of watch and count along with me when you can. The way the electrons fill the orbitals, they fill in such a way. We always start with the first electron. So it's going to be energy level 1, sublevel S, 2 electrons. So 1s2. After a second electron comes electron number 3 and 4, 2s2. After electron number 4 comes electron number 5. That is energy level 2p6. After number 10 comes electrons 11 and 12, 3s2. 12, then comes 13, 3p6. After number 18 comes number 19, 4s2. After number 20 comes 21 through 30, and those are in 3D. So 3D, 10. D, right? Now back up here to 4p6. Energy level 5, S2. Energy level 4, D10. Energy level 5, P6. Energy level 6, S2. And then we have to go down to the F sublevels because after electron 56 comes electron number 57. So we were at 6s2. Now we're at 4f14. After number 70 comes 71, 5d10, and then 6p6, and then 7s2, down to the F, so 5f14, 6d10, 7p6. So I'm going to go through this just a little bit faster in a minute, and then we are going to write an electron configuration, a couple of them from your notes together. Okey-doke, one more time through together, and then I'll write a couple of electron configurations with you, and then we will end this because the recording is getting a little bit long. So, remember we moved helium over here, or the electron over here. So, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p6, 7s2, 5f14, 6d10, 7p6. So if you look in your notes, the first example is asking you for the electron configuration for sodium. So again, we always have to start at electron number 1, and we stop when we get to, for sodium, electron number 11. So if we look at that, the electron configuration for sodium is going to end right here. It's going to end in 3s1. So if we write the electron configuration, we start with number 1, 1s2, 2s2, 2p6, 3s1, and that is the electron configuration for sodium. 1s2, 2s2, 2p6, 3s1. And then you would follow through with the other elements that are in your notes. I don't remember actually what else is there. I don't necessarily have that. Let's see. Chromium is next. So chromium, right here, element number 24, in its neutral state, it has 24 electrons. So if we're writing the electron configuration, start with electron number 1, stop when you get to electron number 24. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4. The electron configuration for chromium again, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d4 is how it ends. So strontium is next. Strontium has 38 protons, and in a neutral atom, it has 38 electrons. So again, we start with electron number 1, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. So strontium ends in 5s2. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. Now, that's starting to look pretty long. Please remember there are no commas, there are coefficients, there are lowercase letters, and there are superscript numbers, which represent electrons. And your electrons should always add together to equal the number of electrons in the atom or ion. So here we have 6 plus 2 plus 2, that's 10. Here's another 20, 30, 36, 38. Strontium had 38 electrons that we needed to put into an electron configuration. So yeah, it gets really long. There is a way to do a shorthand version. I am not going to cover that in the video or in this recording, so if you have questions about that, you should ask me. So what you need to do is finish up your notes with these examples, and then the ones that say you try these. And that is using your periodic table to write electron configurations.